Welcome. In this video I'm going to show you how you can perform a Neyman Goodness-of-Fit test using R. Um, and I'm using Jupyter Notebook, but the R code should also work in, for example, R Studio. I'm using R version number 4.3 with the default packages installed. This video will focus simply on how to perform the test, not so much if you should. There are plenty of alternatives, and this is one that's perhaps a little bit more niche. To show you how this can be done, I need some example data, so I'll load some data in from the General Social Survey of 2012, slightly adjusted for some example purposes. I need one nominal field, so I'm going to be using the marital field, which was MAR1, and just to give you a quick indication, the counts I can store using table. I have a separate video on how I quickly do this with my own library, where I simply have a function that can actually immediately run the test. But in this video I'll show you how you can do it without my library. There's one other library that I'm aware of that could perhaps actually do this test. It's the MSC Quartets library. Now for some reason it doesn't want to expand that section. Now hopefully it does. So you need to install that library and then you can load it. It has a power divergence function actually that will require the expected counts, which if you don't have any specific values is probably just the sample size divided by the number of categories. Number of categories we can obtain by just taking the length of that table we made earlier with the counts. The sum of those will be the sample size, and then the expected counts will be the sample size divided by the number of categories, repeated the number of categories times. Now we can use that power div stat function, and we actually then get the chi-square value. The degrees of freedom is simply the number of categories minus 1. And then finally we can actually just use p chi-square, which will give us the cumulative distribution function. We don't want the lower tail, we want the upper tail. And in this case it's close to 0. It's not actually 0, it's 0.00 something, and therefore we would reject the null hypothesis that all the counts would have been equal in the population. You could also, of course, do it without any library. So we already saw how we can get the table, the frequencies, the number of categories, and the sample size. The expected counts, just as before. And then we can just fill out this formula. It's the sum, so that's this one, of the observed counts, so that's that one, minus the expected counts, that's those. That then all gets squared, so we square those results and then we divide by the counts. And that's our chi-square value, the same one that we saw earlier. The degrees of freedom, again, is the number of categories minus 1, and then we can use p chi-square and actually get that 0 again. There are some corrections, so for example there's the Pearson, the Williams, and also a Yates. So if you want to do the Pearson correction, we simply do n minus 1 over n. And for Williams, we fill out this formula. So that's 1 plus k squared. So that's 1 plus k squared minus 1 over 6 times n times the degrees of freedom. And that's an adjustment factors. So we take the original chi-square and we multiply it with those factors, or for the Williams, we divide it by it. And that then gives slightly adjusted chi-square values. The Yates, we can simply say if the observed count is bigger than the expected, we subtract a half, otherwise we add a half, or if they're equal, that's what I would suggest, is we don't actually do anything. So we can do that in one go with all of this, and then sort, and then calculate the new chi-square value. Alright, I hope this video was helpful, and thank you for watching.